Welcome to this movie on the Kepler Problem. My name is Jos Thijssen and I teach classical mechanics for second years applied physics students at Delft University of Technology. In fact, I've made two more movies on the Kepler Problem, but they are much more extensive, so here I want to go through the same analysis but at a somewhat higher speed. So I hope you will enjoy the movie. As a final step in this description, I would like to emphasize that what we have arrived at is an equation of motion of a one-dimensional particle. It's described by the one-dimensional coordinate r, and its force is given just by the gradient of a potential, and that means that the total energy of this particle, which is the kinetic energy plus the potential energy, should be constant in time, and that turns out to play a key role when we want to solve for the shape of the orbitals, especially in the case of Kepler's problem. The two-body problem in classical mechanics describes the motion of two particles orbiting around each other. The particles are called m1 and m2, those are their masses. The positions are r1 and r2, and they interact via a potential which only depends on the distance between the two particles, so that's r2 minus r1, length of that vector. And that vector will occur more often, so we call it r, and its length is called r without a vector sign. The force on particle 1 is minus dv dr1, and it can easily be shown that this is minus F2 in agreement with Newton's third law. So we'll analyze this problem in the formalism of the Lagrangian. The Lagrangian is given here as the total kinetic energy of particle 1 and 2, minus the potential energy. And so it seems useful to use the r, which is the relative coordinate, the length of which occurs as the argument of v, as one coordinate. On the other hand, we know that for such a problem the total center of mass velocity will not change, so we introduce the center of mass coordinate, which is given as m1 r1 plus m2 r2 divided by the total mass. So recall that m is always m1 plus m2, and we have a relative coordinate r, which is r2 minus r1. And it's useful to rewrite now the r1 and r2 in terms of this capital R and the lowercase r. So here I have done that. So we have written r1 in terms of the capital R and the lowercase r, and the same for r2. And from these two equations that transition is rather straightforward. Now if you have those, you also know what the velocities are. You simply put dots over all the r's, and then you get these two lines. And now we are ready to attack the kinetic energy and to rewrite it. It's now given in terms of r1 dot and r2 dot, and we want to write it in terms of capital R dot and lowercase r dot. So that is what I have done here. I have substituted for the r1 dot here the expression above, and the same for r2 dot, which I have replaced by this. And then we first have a term which is proportional to the capital R dot squared, and that term is easy to see. It's m1 plus m2 divided by 2. Then we have a term proportional to r dot, capital R dot, lowercase r dot, and that has a prefactor of m1 m2 over m and a minus sign. And from this I have a similar term, but that occurs with a plus sign. These terms are equal but opposite, equal in magnitude, opposite in sign, and so they nicely cancel. And then finally I have a term proportional to the little r dot squared, and we see that here we can extract a factor m1 plus m2 from the parenthesis, and that allows us to streamline the equations a little bit. So first we have the term capital M over 2 capital R dot squared, and then there is a term r half. So if I extract a factor of m1 plus m2, that cancels against one of the m's in the denominator, and so what I'm left with is m1 m2 r dot squared, and I'm going to write this as follows. The first term is simply copied, and the second term is written in the form mu over 2 r dot squared. Mu is known as reduced mass, so it's defined as this m1 m2 over m, capital M, and you can easily recall what it is by remembering 1 over the mu is 1 over the little m1 plus 1 over the little m2. So we can write up the Lagrangian now in terms of the capital R and the small r. So these are the kinetic energies, and here we have the potential. So we recall now that the center of mass kinetic energy is constant because the r dot, the center of mass velocity, is constant. So the first term is just a constant, and we can leave that out of the problem. And so the interesting part is the Lagrangian of the relative motion, and that is just the last two terms. Another important remark is that we have now a 2D problem, and the problem is only 2D because there is a plane which is defined by the vector r initially, so that's the relative position of the two masses and their velocities. So if we draw a picture, then the two masses are lying in this plane, and that plane is furthermore spanned by the initial velocity of the relative coordinate. And if because the force is only along the line of the two particles, it's not pointing outside of this plane, and therefore this motion is in 2D, and we can use polar coordinates for the relative coordinate, so in particular for this kinetic energy. So let's do that. So we leave out the first term because it's constant, and we can now write the L as mu over 2 r squared with a dot plus r squared phi dot squared minus VR. So we can write up the Lagrange equations, and we can start with the Lagrange equation for r, which is given as d dt, and then we have the L, the r dot. That is the same as mu r dot dot, and then we have the derivative of L with respect to the little r. But we have of course first this term, but there is an additional term, and that term is coming from this r here. We shouldn't forget that. So there is an extra term which is mu r phi dot squared. And so in order to get a handle on the phi dot squared, it's useful to calculate or to write down the Lagrange equation of motion associated with the coordinate phi. So that's what I've done here, and we see that there is a conserved quantity because the time derivative of the term in parentheses is 0, and we recognize that term as the angular momentum perpendicular to the plane. So this is Lz, and that's a kind of r cross p for the relative motion. So that is a conserved quantity, as we could expect, because there are no external forces, and then the angular momentum is conserved. So calling this conserved quantity little l, we can remove the phi dot from that equation using the definition for L. It's mu r squared phi dot. And so we can replace phi dot by something which depends on L, mu and r, and if we do that properly we get a plus L squared divided by mu r to the third. And so we see that mu r dot dot can be written as the direct force that the particles exert on each other, and a term related to the angular momentum, and this is in fact a centrifugal force because the two bodies are orbiting around each other. And so let us, as a final step here at this stage, try to write this as the gradient of just a single potential, because that's possible. We can write this as VR in parentheses, and then we would get a plus L squared over 2 mu R squared. And so we see that we can write this as a single potential, which is called the effective potential, which is the direct interaction term between the two particles, and there is a term associated with the centrifugal force, and that's a centrifugal barrier, the repulsive barrier between two particles. As a final step in this description, I would like to emphasize that what we have arrived at is an equation of motion of a one-dimensional particle. It's described by the one-dimensional coordinate r, and its force is given just by the gradient of a potential, and that means that the total energy of this particle, which is the kinetic energy plus the potential energy, should be constant in time, and that turns out to play a key role when we want to solve for the shape of the orbitals, especially in the case of Kepler's problem. So now we want to apply the fact that the energy is constant and the fact that the angular momentum is also a conserved quantity to the particular case of the Kepler problem, where it enables us to find exactly the shape of the orbitals that orbits that particles will traverse when they orbit around each other. So the Kepler problem is characterized by a potential which is minus a constant divided by r being the distance, and a is a positive constant, and it describes the important cases of gravity, for example the planets orbiting around the Sun, and the Coulomb problem, for example, of an electron orbiting around the nucleus of a hydrogen atom. So we emphasize again that we have two conserved quantities, one being E, which I will write again, it's mu over 2 r dot squared, and now I will write the V effective explicitly. It's minus the plus the V as a function of r, so that's my minus a over r, and then there is an additional term which is L squared over 2 mu r squared, and the L is also a conserved quantity, it's mu r squared phi dot. So these two guys are conserved in time. So the trick in order to find the shape of the orbitals is to find out what d phi dr is, rather than to find phi and r themselves explicitly as a function of time. And that can be written, d phi dr can be written as phi dot divided by r dot, since they are both functions of time. And if I then plug the r dot from here and the phi dot from there in, I get this equation, and if I streamline that a little bit, it acquires this form. And then we note that this can be rewritten essentially in the following way. So doing away with all the constants and replacing them by a and b, we get this form, and that is an integral we can in fact do. And it turns out that the result is the following: r is L squared divided by mu times a, which is the prefactor occurring with the 1 over r potential, and then a 1 minus epsilon sine phi minus some constant. So c is an arbitrary constant. That's not the case for the epsilon. The epsilon which I have introduced here is the square root of 1 plus 2 el squared divided by mu a squared. Now you should of course first of all distinguish between the two cases. First is E is greater than 0. That means that we don't have a particle orbiting around the center, but it will fly away because the kinetic energy is apparently bigger than the potential energy, and so in that case we have epsilon greater than 1, and it turns out that this equation then describes a hyperbola. If E is equal to 0, that's just the point where the particle can just escape. That corresponds to epsilon equal to 1. We have a parabola. And for the case where E is smaller than 1, we have an ellipse. Then there is another special case, and that is the case where epsilon, so this is the case for negative energies, and if epsilon equals 0, then we have a circle, and you can easily see that from the solution. If epsilon is 0, you see that r is constant, so it doesn't vary with the phi, and that's typical for a circular motion. So here you see a simple Python program which I wrote in order to solve the equation of motion for a particle in 2 dimensions, and I will show how that program works for the Kepler problem. So I will not go into the details of the Python or of the plotting part of this program, but just focus on the dynamics, which tells you how the particle's positions evolve. The position is encoded into a vector r, which is 2-dimensional. The velocities are given by the vector p, momentum also 2 dimensions, and I take the mass equal to 1, so p is just the velocity in this case. The initial conditions are that the particle is released on the x-axis at 1, 0, and it leaves the x-axis with a velocity in the y direction of 0.4. The solution proceeds by moving the particle step by step, and the time elapsing between 2 time steps is 0.0005. Now I take the Kepler force, the gravitational force, as -1 over r, so the prefactor is simply -1, and if I calculate the force from this potential, I get minus the vector r divided by r to the third, and you see that that is encoded here in this function which calculates the force. So we have minus r divided by r to the third. Then the actual solution takes place in this part of the program, and it's done in the so-called velocity-Verlet algorithm, which I will not go into in detail, but it's a very simple and accurate way of solving equations of motion. Of course, the part which really determines the shape of the orbit is the call to force. If I would change the force, I get different motion. And so it is interesting to see what we get from this program. So when I press the enter key, the program starts running, and we see that we get a perfect ellipse, which is quite eccentric, and it's so this is the attraction, the center of attraction. This is the origin, and we see that the particle passes very close by the attraction center. The orbit is a closed ellipse, and this ellipse is traversed several tens of times, but we do not see that because it's each time the same orbit, so you don't see the particle really moving. So it is interesting to study the case where the force is not a pure Kepler force, but where it's slightly distorted. As you can see here, I have introduced a parameter eta, which I will take small, and it gives you a distortion from the gravitational potential. And the force that I can derive from this, it's also an easy calculation, it's 1 plus eta r divided by r to the power 3 plus eta. So the only thing which I changed in the program, the only essential change, is this introduction of the parameter eta, which I've done here according to this formula. And so it is interesting then to see what happens. I will take the eta first 0, so then we get the previous case where we have a pure Kepler orbit, and that's drawn in blue. Then we will see the orbit for eta equal to 0.01, and then I will take eta minus 0.01, and that will, the last two will be respectively a green and a red curve. Okay, so let's see what we get when we start the program. First we see obviously the blue curve, just as before, the closed Kepler orbit, because that was the case where eta was 0. Then the green curve, you see that it's no longer a closed orbit, but it's a precessing ellipse, and it precesses in the positive y direction. Then the red curve corresponds to eta minus 0.01, and that gives me a curve that precesses in the negative y direction. So you see that the fact that the orbit is closed in the Kepler case is really a special feature of the form of that potential, which is the 1 over r potential. So let us enjoy the beautiful picture once again. Here you see the closed blue curve and then the precessing green and red curves, which correspond to a slight distortion from the pure gravitational force.